All right, let's dive right in. Welcome to the Explainer. Today, we're pulling from Lecture 20 by Skip You and I to officially kick off Episode 2 of our C++ series, Mastering Control Flow. In our first session, we laid down that essential groundwork. Variables, constants, operators, basic I/O. That was basically our vocabulary. But today we step into the realm of dynamic, smart logic, where your code actually transforms from a boring, static list of commands into this intelligent decision-making entity. Here's a quick look at our agenda for today. First up, beyond sequential execution, then defining control flow, making decisions in code, repeating tasks with loops, and finally, jump statements. Let's get right to it.
Section 1, Beyond Sequential Execution. To start us off, we need to understand how a computer naturally reads your code right out of the box. Imagine you've written a basic C++ program. If you don't add any special logic, the computer executes those instructions strictly sequentially. Line 1, then line 2, then line 3. But does code always have to run line by line? The answer is a resounding no. Real life doesn't just happen in a strict, unchangeable sequence, right? And our program shouldn't be restricted that way either. Simple sequential execution is fine for super basic tasks, but complex software, it demands flexibility. Sometimes you literally just need to jump from line 1 straight to line 10, or maybe skip a whole chunk of code entirely. And you can see that contrast right here. On one hand, you have that default, rigid, step-by-step execution. But on the other, you've got the reality of what complex programs actually need: dynamic execution. It's highly flexible. It's the kind of magic that allows a program to react to user input, process data intelligently, and handle totally unexpected situations without just crashing. We really need a way to break out of that default sequence.
Section 2, defining control flow.
Which brings us to the exact mechanism that solves our strict sequential problem: control flow. It is the ultimate tool that empowers you to manage and dynamically alter the execution path of your instructions. Basically, you become the traffic director of your code. You're no longer at the mercy of just reading top to bottom. And C++ gives us 3 very specific categories of statements to actually pull this off. Section 3, making decisions in code. Let's break down this first major branch, teaching your code how to make choices. This right here is what truly makes a program smart. To control the flow based on specific conditions, C++ gives us selection statements. We're talking if-else, nested if, and switch commands. They are your foundational tools for creating branches in your code's logic. So depending on whether a condition is met, like, say, a user entering the correct password, the program will automatically just select one path over the other. Honestly, to really grasp if-else logic, just think back to being a kid. We've all heard this classic childhood condition. If you get a certain percentage of marks on your exam, you get a gift. Else, you're getting a slap or a scolding. It's a harsh but literally perfect binary outcome based on a single condition. One block executes if it's true. Otherwise, well, you face the else block. And this builds a highly logical step-by-step process right inside our code. Step 1. The computer evaluates the condition, checking those marks. Step 2, if that condition evaluates to true, it executes the if block, handing out the gift. But step 3, if it's false, it bypasses that gift entirely and executes the else statement, delivering the scolding. It's a direct, real-life mirror of exactly how C++ selection statements operate.
Section 4, repeating tasks with loops.
Moving on to our second category, we tackle scenarios where a specific task needs to happen over and over and over again. Decision-making is great for picking a path, but what if you need to walk that path 100 times? Well, if you have a task that needs to be executed repeatedly, you absolutely do not want to write the exact same code manually every single time. Imagine needing to print the numbers 1 through 1,000. Typing that out 1,000 times? It's inefficient, it's prone to typos, and frankly, it's a nightmare. That is exactly where loops step in to save the day. Instead of doing an exhausting sequential copy-paste operation, you simply wrap your logic inside a loop. You write the block of code once, and you basically tell the computer, hey, keep doing this exact thing until a specific condition is met. It continuously runs, repeating the task until that exit condition finally evaluates to true. Once it does, boom, the loop stops and the program seamlessly moves forward.
Section 5, jump statements.
Finally, we reach our third pillar, which allows for abrupt, deliberate changes in direction. Because sometimes standard decisions and loops just aren't enough. You might need an emergency eject button. Commands like break, continue, go to, and return, these are your jump statements. They actively force the program to abandon its current path and instantly teleport somewhere else. Like, for instance, if you're searching through a massive loop and you suddenly find your target data, you don't want to keep looping pointlessly, right? A break statement instantly shatters that loop so you can jump out and just move on. So this explainer has laid out your high-level roadmap. We've contrasted rigid sequential execution with dynamic control flow using decisions, loops, and jumps. But theory is really only half the battle. In our upcoming explainers, we're going to open up the code editor and actually see these exact skip-uni concepts executed live in C++. As we wrap up today, I want you to realize that mastering these statements completely transforms you from just a typist into a true architect. You aren't just making static lists anymore. You are breathing logic and intelligence into your applications. So, my final question for you is this. Now that you can dictate exactly how your code thinks and behaves, what complex problem are you going to force it to solve first? Think on that, and I'll catch you in the next explainer.